in this video, we'll talk about the inverse of a matrix. So first of all, suppose you have a real number equation like 5x equals 20. Right, so one way to solve an equation like this would be first to multiply both sides by 1/5, right, because we want to cancel out the multiple of 5. And so you basically divide by 5, or equivalently multiply by 1/5, right? So multiplying both sides by 1/5, it cancels out the 5, and then you get x is equal to 4. So basically, that's because 1/5 is the multiplicative inverse to 5, and it cancels out the 5 on the left. However, if we have a similar kind of matrix equation of the form ax equals b, where a and b are known matrices, and we want to solve something similar, you can't simply just divide by matrix A, right? Because matrix multiplication is more complicated than ordinary multiplication, and so there's really no operation of division for a matrix. And so what we want to try to find is what's called the multiplicative inverse for a matrix. And that's what we discuss in this section. Okay, so the inverse of a matrix, first of all, the original matrix has to be a square matrix for the inverse to exist. Right, so we're only dealing with square matrices here. And so if A is invertible, then there has to be another matrix B such that A times B or B times A both result in the identity matrix, because the identity is the identity matrix plays the role of 1 for matrix multiplication. Right, so we want to be able to cancel out a matrix and get back the number 1. So if we can find this matrix, then this is called the inverse of A. A matrix that has an inverse is called invertible or non-singular, and a matrix that does not have an inverse is called non-invertible or singular. So again, for a matrix to possibly have an inverse, it has to be a square matrix. But just because a matrix is square doesn't necessarily mean that it has an inverse, right? So some matrices have an inverse, some matrices do not have an inverse, as we'll see in this section. Okay, so however, if a matrix does have an inverse, then the inverse is unique, right? So basically means if it has an inverse, it can't have different inverse matrices, so there's only one way of getting the inverse. So a statement like this isn't too hard to prove, right? So basically it means that, again, if a matrix has an inverse, then it can't have different inverses, right? So to prove it, basically you just have to show that this has to be true, right? So you suppose that A is an invertible matrix, and B and C are two inverses to A, right? So you can't possibly have two different inverses, right? So that must mean that B and C have to be the same. So basically that's how you prove this statement here. Okay, so basically what you want to do is to use the various properties of inverses to reach exactly this conclusion. Right, so how do we do that? So first of all, let's start with the fact that B is an inverse to A, right? So what does it mean for B to be an inverse? Exactly this thing here, right? So if I multiply A times B, I get the identity matrix. So this is just from the definition of a matrix inverse. Okay, so So I have that A times B is the identity matrix, and suppose I multiply both sides of this equation on the left by C. Right, so I multiply both sides on the left by C. And then now let's apply the associative property of multiplication to move the parentheses. And then anything times the identity just gives back the matrix, right? So C times I, the identity is just C. But again, C is also an inverse to A. Right, so that means that from the property of inverse, when you multiply inverses to each other by itself, it should cancel and I get the identity matrix. Right, so C times A is just the identity matrix. But then identity times B is just B, and so this shows that B is equal to C. So again, basically this shows that if you were to start out with two inverses B and C, they should have been the same all along. Right? So that means that you cannot have two different inverses. And so this proves the theorem that the matrix inverse is unique. Okay, so we want the matrix inverse to cancel out the original matrix, right? So how do we get the matrix inverse? Well, for a 1-by-1 matrix, it's pretty straightforward. So a 1-by-1 matrix is just a number, a single number in that single entry, right? So it's basically just behaves like a real number, right? So the inverse of some number A is just the reciprocal, as long as A is not equal to 0, right? Basically because multiplying single 1-by-1 matrices is just the same as multiplying real numbers. Right, so a number times its reciprocal cancels out and you get 1. Which is the 1-by-1 identity matrix. Okay, so 1-by-1 matrix is pretty straightforward, but what about larger matrices? So for a 2-by-2 matrix, we'll see that it's a little bit more complicated, right? So first in this example here, I claim that B is the multiplicative inverse for A, right? So what does that mean? That means that if I multiply them together, I should get the identity matrix, right? So A times B should be the identity, and B times A should also be the identity matrix. It doesn't matter which order you multiply them in, if you should get the identity matrix. Okay, but before we do that, if you compare the matrices A and B, you can see that there's not really any clear relationship between the entries of A and B. I mean, there's a 7 here and there's also a 7 here, but it's not completely obvious what the relationship between the entries are. So finding the inverse for larger matrices is slightly more complicated. But in any case, let's just check that the matrix B I have here is actually the inverse. By just doing the multiplication. Okay, so A times B is 4, 7, 2, 4 times 2, negative 7 halves, negative 1, 2. Alright, so let's just do the multiplication. Right, so it's 4 times 2 plus 7 times negative 1 for this first entry, and then 4 times negative 7 halves plus 7 times 2. And this entry here is 2 times 2 plus 4 times negative 1. This last entry would be 2 times negative 7 halves plus 4 times 2. And now when we do the calculation, right, so this is 8 minus 7, which is 1. This is 4 divided by 2 is 2, times negative 7 is negative 14. So negative 14 plus 14 cancels out, so that's 0. It's 4 minus 4, which is 0. And then this is negative 7 plus 8, which is 1. Okay, which is, this is the identity matrix, so that checks out. And then now we multiply in the reverse order. And we'll see that, again, you get the identity matrix. Okay, so let's do the multiplication. 2 times 4 minus 7 halves times 2. The next entry is 2 times 7 minus 7 halves times 4. This entry is negative 1 times 4 plus 2 times 2. And this entry is negative 1 times 7 plus 2 times 4. And then calculating the entries is 8 minus 7, which is 1. 14 minus 14, which is 0. Negative 4 plus 4, which is 0. Negative 7 plus 8, which is 1. Okay, so that also checks out. Okay, so we see that A and B are inverses to each other. But again, what is actually the relationship on their entries? So we'll see that what the relationship is in a second, right? So in general, if you have a 2 by 2 matrix, so I call the entries A, B, C, and D. So first of all, A is invertible exactly when AD minus BC is not equal to 0. So kind of like when you can't divide by 0, right? So this thing is called the determinant. And so when AD minus BC is not equal to 0, the inverse of the matrix is given by 1 over AD minus BC. So this is the scalar multiple, and the entries are like this, right? So you switch the entries on the diagonal, right? You switch A and D, and then B and C stay in the same place, but you take the opposite. So the opposite of B and then the opposite of C. And so this will give you the inverse of the matrix A. And you can check that this is an inverse by multiplying these two things together, right? So here I've taken these two things and multiplied them together, and if you check the calculation, it does give you the identity matrix. So this is the inverse for the general 2 by 2 matrix. Okay, so let's take a look at an example of finding the inverse for a 2 by 2 matrix. Right, so here we have this 2 by 2 matrix, 1, negative 2, 2, negative 3. So this is A, this is B, this is C, this is D. Okay, so first we want to check if the inverse exists by calculating AD minus BC. Okay, so AD minus BC. So AD is 1 times negative 3. And BC is negative 3 times 2. Right, so what do we get? Oh, sorry. B was was negative 2, right? So negative 2 times 2. So AD minus BC. Okay, so that's AD minus BC. And, okay, so what do we get? This is negative 3. AD minus BC. So this should be a minus. So negative 3 minus a negative 4, which is negative 3 plus 4. So AD minus BC is equal to 1. And so now we can find, so this is not equal to 0. So inverse exists. So now we can find A inverse, right? So it's 1 over AD minus BC. And then again, A and D switch places, right? So D and A. And then B and C stay the same, but have opposite signs. So AD minus BC was 1, right? So this is 1 over 1. And I switch these two. So negative 3 and 1. And then these have opposite signs. So this becomes a positive 2. This becomes a negative 2. So I get negative 3, 2, negative 2, 1 as the inverse matrix. Okay, so it's always a good idea to check if you have the right inverse, right? So A inverse times A should give you the identity matrix. Right, so let's check by doing the multiplication. So this entry is negative 3 plus 4. This entry is so this should be in the negative 3. Okay, so the next entry is 6 minus 6. And this entry is negative 2 plus 2. Find the last entry is 4 minus 3. So what do we get? 1, 0, 0, 1, which is the identity matrix. So this checks out. Okay, so for a 2x2 matrix, again, basically we just need to use this formula. For 3x3 and larger matrices, the inverse matrix can be determined by Gauss-Jordan elimination using a modified augmented matrix. But for now, we can just use a calculator to determine the inverse. Right, so if I want to find the inverse, right, so to save time, I've already entered the matrices into the calculator, but you enter in the matrix as you usually do, right? So press second and then matrix, and then in edit, you input in your matrix, right? So this is my matrix A, and then now to calculate the inverse, right, you choose the matrix under name, and then on the main screen, right, so you see how the inverse is raising to the -1 power, right? So I can just hit this key, x to the -1. And you can see now it looks like A inverse, right? And if I hit enter, it'll calculate the inverse matrix if it exists, right? So you see this is the inverse to matrix A. And you can see that this is the inverse, right? Because if I do A inverse, then times A, you get back the identity matrix. Okay, so this is how you find the inverse. But what happens when the inverse of a matrix doesn't exist. So you'll see in the example for matrix B, so I've already again entered it into the calculator. If I try to find, so again, B is this matrix. If I try to find the inverse for B, so here I'm trying to calculate B inverse. So I got an error where it states that B is a singular matrix. So the again, singular means it's not invertible. And so in the case where the inverse of a matrix exists, it'll produce this error. Okay, so this is for 3x3 matrices, but larger matrices, again, you can just put it into the calculator like this. Okay, so this page discusses some of the properties of inverse matrices. So the four that are listed here are fairly straightforward, right? So the first one says that the inverse matrix to A inverse is the original matrix A. So that's just from the definition, right? Because if B is the inverse to A, then A has to be the inverse to B just from this equation here. Okay, so the first one is fairly straightforward. The second one says that if you raise a matrix to a power and take the inverse, it's the same as first taking the inverse of A and then raising it to the power. So that's also fairly straightforward. But you can see an example here, say on a calculator, right? So the matrix A was invertible, right? So if I take A, say, to the third power, so I get this matrix here. So if I take A, say, to the third power first, how do I insert? And then take the inverse. That's a pretty big matrix. That's because there's rounding error here. But in any case, this is A cubed inverse, but what if I take so parentheses A inverse and then raise it to the third power? So it looks a little bit different, but it's actually the same, right? Because of rounding error. So negative 35, then negative 27, then 57 down the first column, then 19, negative 1, negative 12 in the second column. I can't seem to scroll to the right, but you can see that they're the same matrix. Okay, and then it's so similar. If you take the transpose first, and then the inverse is the same thing as taking the inverse first and then the transpose second. So the one we want to pay attention to is this property here, where the inverse of a product, where it's similar to the transpose in that when you try to distribute the matrix inverse to a product, it reverses the order of the matrices. Right, so that's basically because of the following. If you try to multiply the individual matrices by their inverses, they have to be in this order for the cancellation to occur. Right, so you see how if I have the matrix product A times B where A is on the left, you would first have to cancel A on the left by A inverse. Right, so they'll essentially cancel this out, and then I have to have B inverse farther to the left. Right, so for the inverses, it has to be in this order. Okay, so this is just saying that cancellation on the left is different from cancellation on the right. So because of the property of matrix multiplication, right? So be careful whether you want to cancel on the left or cancel on the right. Okay, so the final property here relates the matrix inverses back to systems of linear equations that we've dealt with previously, right? So if you have a system of linear equations represented in the form ax equals b, where x is a column vector and b is a column vector, and A is a square matrix. So if A happens to be an invertible matrix, you can cancel A on the left by A inverse, and that'll allow you to solve for x. So again, basically it's just multiplying by A inverse on the left, and that'll cancel this out, and so you get x equals A inverse b. So this gives another way to solve systems of linear equations, at least in the case where A is an invertible matrix. Okay, so let's try to solve a system of linear equations by using the matrix inverse. Right, so first what you want to do is, for your system of linear equations, you need to put it in matrix form. Right, so the matrix A is just the matrix of coefficients. Right, so you see that all the x's, y's, and z's are lined up, so it's in standard form. Right, so I can just read off the coefficients. So 2, 3, then 1, then 3, 3, then 1, then 2, 4, 1. Then the column vector for the variables, right, so x, y, and z. And then on the right hand side is the constant terms, so 4, 8, and 5. Okay, so this represents A, this represents X, and this represents B. Right, so the matrix is in the form AX equals B, and then we solve it by taking the inverse. Right, so I've already inputted the matrix A into the calculator. Right, so you can see when I calculate A inverse, it gives you exactly this matrix here. Right, so negative 1, 1, 0, negative 1, 0, 1, 6, negative 2, 3. So this is our inverse matrix, and then now to calculate the solution x, we can just multiply A inverse by this matrix B here. Okay, so I take A inverse, I enter in my matrix B, so B is a 3 by 1 matrix, right, so the entries are 4, 8, and 5. Right, so A inverse was the previous calculation, right, so I can just take that and multiply by the matrix B, and I get 4, 1, negative 7 as my x, y, and z. which is exactly this many. And then you can, you can plug in x, y, and z back into the original equations. You can check that it works out. Okay, so we can solve these kinds of systems like this, but the downside of this method is that this only works when A is invertible, right? So in the case where A is singular, and you can't find the inverse, it's not immediately clear whether what happens to the system is that whether there's no solutions versus infinitely many solutions, right? So usually when you're solving equations, still the method of finding the reduced row echelon form is better. One possible use case of this is if you know that the system does have a non-singular matrix A, and you need to solve many different systems where the constant terms are changing, then maybe this method is better.